Previously, we learned about the basic principles of magnetic resonance using the example of the mechanical resonance of a rotating wheel. And we related that to the idea of atomic nuclei with their magnetism and their angular momentum precessing in a magnetic field. Now we're going to carry out a nuclear magnetic resonance experiment using the Terra Nova apparatus behind me. Remember the two principles that we need to consider when we're thinking about magnetic resonance. We've got to have a static magnetic field, and that's provided by the Earth's magnetic field, which is about 60 microteslas and leads to a Larmor precession frequency for hydrogen nuclei of just over a couple of kilohertz. And the second thing we need, of course, is that transverse oscillating magnetic field, which is provided again by the probe of the Terra Nova apparatus. Of course, we're going to need a sample, and the sample we're going to use today is water. I guess I should try to convince you first and foremost that it really is water. So let me just taste some of it. It definitely seems like water to me. So what is water made up of? Well, it's made up of molecules a bit like this. An oxygen atom, which at its heart has a nucleus, which actually has no magnetism and no angular momentum and plays no part whatever in the nuclear magnetic resonance phenomenon. But attached to the oxygen are two hydrogen atoms, and at the heart of those hydrogen atoms are atomic nuclei, which we call protons. And there's a large abundance of these water molecules and lots of protons available in the water sample that we're going to prepare today. Actually, the water molecules are a little more complicated than that because the hydrogen atoms tend to jump from one molecule to another, but we needn't concern ourselves about that. There's an enormous number of water molecules in a container of water like this. In fact, there are more molecules of water in this bottle of water than there are bottles of water like this in all the oceans. That's really a gigantic number. So we're going to have plenty of atomic nuclei and plenty of nuclear magnetism to play with. So let's prepare the sample. This is the container that we're going to place inside the probe of the Terra Nova apparatus, and I'll just fill it up with water from this bottle. By the way, water is not the only material that one can perform nuclear magnetic resonance experiments on. There's lots of other molecules around that contain plenty of hydrogen. For example, I've got sitting over here a very different sort of molecule. It's an aliphatic chain, such as you might find in one of the lipid molecules in your body. Lots of carbon and lots of hydrogen. In fact, any material that contains hydrogen, particularly when it's in a liquid form, is really quite suitable for carrying out a nuclear magnetic resonance experiment in the Terra Nova apparatus. So now we're ready to carry out our very first nuclear magnetic resonance experiment on the Terra Nova apparatus. Remember, we're going to start with that pre-polarising pulse to produce some larger magnetisation, and then we have to disturb the spins from their thermal equilibrium state. And for that we use the transverse oscillating magnetic field, which is inside this probe. And we apply that for a short period as a pulse. We're just waiting now while the pre-polarising is going on. And now we have the excitation and the decay of that oscillating signal, the free induction decay, over a period of about 0 to 2 seconds. Let's zoom in on that free induction decay and see if we can see the oscillation. There it is. A very clear oscillation revealed over this shorter time window. So that's known as the time domain. If we perform a Fourier transform on that time domain data, we get the spectrum. And that spectrum lies in the frequency domain. And in the right-hand panel, we can see that spectrum. It corresponds to a definite peak, which is centred at about 2.17 kilohertz. I said before that the precession frequency was about 2.5 kilohertz. Of course, it varies from place to place on the Earth's surface. Down in Antarctica, it's about 2.6 kilohertz. And here in Wellington, it's just under 2.2 kilohertz. So that's the free induction decay from a water sample. Really, we should check if this is real. I'm going to remove the water sample and we'll run this experiment again and see what happens. Repolarizing pulse. No free induction decay, just noise this time. We really are getting a signal from this bottle of water. So that's the very simplest nuclear magnetic resonance experiment, obtaining the free induction decay. In later videos, we'll look at more sophisticated experiments where we can learn something about the nature of the molecules, something about their dynamics, how they're moving, and in particular, where molecules are, finding their positions. That's the basis of magnetic resonance imaging, and we're going to look at that in some detail.